People often picture black holes as giant cosmic vacuum cleaners, indiscriminately slurping up stars, planets, and anything else wandering through space. In reality, a black hole is simply a region where gravity is concentrated into a small volume. If you swapped our sun for a black hole of the exact same mass, Earth wouldn't get pulled in. We would keep orbiting in the dark. If you actually want to survive a trip inside one, you have to pick your destination carefully. This diagram compares two types of black holes. On the right is a small, stellar mass black hole. It has a steep change in gravity that would tear you apart before you even got close. On the left is a supermassive black hole. Because it is so huge, the change in gravity at its outer edge is gradual, allowing you to cross the threshold in one piece. Approaching our supermassive target from a safe distance, the first thing you'll notice is a glowing ring of matter spiraling around a pitch-black center. This is the accretion disk. It consists of gas and dust caught in the gravitational pull, rubbing together so fast that the friction heats the material to millions of degrees. Surviving a journey into a black hole relies entirely on the scale and mass of the black hole you choose to enter. As you fly closer, the background of the universe begins to distort. The starlight from galaxies behind the black hole starts to smear and stretch. You will even see ghostly, duplicate images of the exact same stars appearing on opposite sides of the black shadow. This optical illusion happens through a process called gravitational lensing. In this cross-section, the immense mass of the black hole physically bends the paths of light traveling from distant stars. The light isn't traveling in a straight line anymore. It takes a curved detour. Move closer to the photon sphere, and light perfectly traps in orbit, creating an intensely bright ring. Extreme gravity exerts its influence on everything, including light. It distorts the optical reality of the universe around you. As you approach the boundary, the gravity begins to alter the flow of time itself. If you look at this split-screen graphic representing time dilation, the clock on the left shows your perspective as you fall. Your wristwatch ticks at a steady pace, and your descent feels normal. But if you look back out at the rest of the universe, represented by the clock on the right, you would see the outside world fast-forwarding into the future. Meanwhile, a friend watching you from a distant spaceship experiences the opposite. Because of a phenomenon called gravitational redshift, they see your movements slow down to a crawl. To them, you never actually seem to cross the edge. You simply appear to freeze in place, gradually fading to a deep red as the light stretching off you loses its energy. Gravity forces the flow of time to diverge, splitting the universe into two contradicting realities. Eventually, you cross the event horizon. You won't hear an alarm, and you won't hit a physical wall. As you glide forward, it is a continuous transition through empty space without any sudden flashes or bumps. The event horizon is a mathematical boundary. It is the point of no return, where the speed required to escape the black hole's gravity exceeds the speed of light. Inside the horizon, the geometry of space changes. Looking at this grid, you can see that all paths now bend and point toward the center. Moving toward the core is no longer a direction in space. It acts like the unavoidable forward flow of time. Inside the horizon, the singularity is no longer a physical place located below your feet. It has become your inescapable future. Even though the supermassive black hole allowed you to cross the horizon smoothly, you are still in danger. The high-energy radiation from the superheated accretion disk is still falling in right behind you, flooding the space with energy. If you survive the radiation, there is a final physical hurdle as you plunge deeper. Astrophysicists call it spaghettification. As you get closer to the center, gravity intensifies over very short distances. In this diagram, notice how the gravitational pull at the bottom is stronger than the pull at the top. If you were falling feet first, your feet would be pulled down faster than your head, causing your body to stretch out like a noodle. The gradient of gravity eventually overpowers the chemical bonds holding your cells together, tearing apart the molecular structure of any physical object. Your journey finally ends at the singularity. This is the absolute center, where all the mass of the black hole is crushed into a single, infinitely small point of vibrating darkness. At this exact point, our current understanding of physics, specifically general relativity, breaks down. The math stops producing logical answers. It leaves us with a lingering question. What actually happens to matter and information when the rules of quantum gravity take over at the very core? The singularity represents a limit to modern human science,